Welcome. In last session we have discussed that solution of Ax is equal to b in the cases where there is no unique solution lie in a vector space, and we stopped our discussion there, and today we will see what a vector space is and how later we will see how these solutions lie on vector space, how are the solutions span over a particular vector space, and how can we obtain the solutions in cases where there are non-unique solution, where there are especially infinite solution and our typically Gauss elimination type of solvers fail for this type of equations. So, what is a vector space? A real vector space is a set of vectors together with the rules of vector addition and multiplication by real numbers. That means that there will be a number of vectors and we can add those vectors, we can multiply a vector with a coefficient, and then also we can add the vectors multiplied by a coefficient with another vector, and the resultant vectors will also lie on that particular space. So, if we see how is it, for example, if we see vectors in a plane, they form a vector space. In order to explain that, we can say that there are two vectors v and w, and we say that they lie in a plane. So, if we do an addition v plus w, that will also lie on a plane, and so this plane is now a vector space where all the vectors are lying. Also, if I multiply w by 2 and we get 2 w, this vector 2 w when added with v, this is 2 w itself lying in the same plane, and v plus 2 w is also lying on the plane. So, all vectors in a which are coplanar can be said that it can be said that they belong to one particular vector space. We will see this in more detail. Coordinate space is a vector space, and this is something interesting and something more real life like. Coordinate space is space spanned by the coordinates x, y or x, y, z in 3 dimensional, or the former was in 2 dimensional case. So, if we think a vector which can be expressed in an or which lies in an x y plane. So, it has a x component and has an y component. So, this is a vector like that, and all the vectors lying in x y plane, they belong to a vector space which is the coordinate space. And a coordinate space or a real coordinate space, because there is no imaginary coordinate here, all the distances measured along a axis in the coordinate plane is a real distance. So, it is given as r with a superscript n, and this is called an n dimensional space when there are n components or n of the vector or n dimensions expressed by that coordinate plane. So, if we see a coordinate plane by x y only, this coordinate plane space gives me a vector space which is R 2, because this is a 2 dimensional space. Similarly, we can think of a 3 dimensional space. Any vector in R n will have n components. So, any vector, before coming into it, any vector, we can see any vector here. For example, this vector is given by x 1 y 1 or x 1 I plus y 1 j, something like that, or a vector here can be given as x 2 and y 2. So, any vector in a 2D space will have 2 components. So, any vector in nth order coordinate space will have n component, and coordinate space is a vector space. So, if I look into a 3D vector, this is a, if I look into a 2D vector in R 2, this is a 1, a 2, b 1, b 2, these are the vectors, and all these vectors will give us a coordinate a vector space which is the coordinate space. And if we look into a 3D vector or 3D coordinate space, there will be 3 axes, because it is a 3 dimensional plane, and any vector will be in that particular 3 dimensional plane or in that coordinate space which is R 3 dimensional coordinate space, and any of these vector will have 3 components. I will require 3 components to express any of these vector. Now, why is this a vector space? Because we can add these two vectors and get a resultant vector which will also lie on the same coordinate space or same vector space. A vector with 3 components can only be added with a vector with 3 components, and the resultant will be another vector with 3 components. So, they lie in the same vector space. Also, if I multiply a vector, it is just magnifying the vector in the same coordinate space, and it lies in the same coordinate space, its same vector space. So, coordinate spaces or the physical geometries with given axis, x axis, y axis, or r axis, theta axis, or r theta phi z axis, or x y z axis, these spaces, 2D spaces or 3D spaces, what we can perceive physically are vector spaces, because any vector in a 2D space can be added with another vector in 2D space, and I will get another vector in 2D space only. So, what is important in defining a vector space, we can also get that if I have a vector with 3 components, it can be added with another vector with 3 components, and this addition, if we add them, so the addition will be a1 plus b1, a2 plus b2, a3 plus b3. That should also have 3 components. It sounds very trivial and kind of an axiom that we can very easily accept it, that okay, 3-dimensional things can only be added to 3-dimensional things. However, this is the basic definition of a vector space, that if we add 2 vectors which they should have same components, and the resultant same, they should have same, if we add 2 vectors they should have same number of components, and the resultant will also have similar number of components, and the space in which first 2 vectors are lying, the resultant vector should also lie there. In 2D and 3D it is apparent. The problem or the more difficulty in perception will probably come when we will go for higher dimensional spaces, and we also have to see why are we doing vector space, how is it related with matrix algebra, we will come into it later. So, the question becomes 2D and 3D we can understand, even 1D we can probably also understand, that is if we move only along x distance, we may measure distance only along x distance, that also gives me a coordinate space which we are now calling as a vector space, that if we can add vectors in that space, we can multiply a vector by another constant and then get another vector in that space only. But how will be R4 or R5 or even higher dimensional spaces which we really cannot perceive using our geometric visualization capacity. We cannot perceive what is a 4-dimensional space, 5-dimensional space, or even higher dimensional spaces. So, how will they be? But we can probably get an idea what says that any vector in n dimensional coordinate space will have n components, and what lies in coordinate space, anything till infinity can lie in coordinate space. I can have a line infinitely long and say in 2D space, 2-dimensional coordinate space or R2, it is tends something which x and y both tends to infinity. Similarly, I can have anything in R3, any 3-dimensional geometry, any 3-dimensional vector or length can be translated into a vector, any length in 3-dimensional geometry can be translated into a vector which is belonging to R3. So, now question comes that what will be R4 and R5. And we will start to look into higher dimensional vector spaces. We will start with what is 0th dimensional vector space. What is 0 dimension? 0 dimension means we say a point has a 0 dimension. What is a point? It has no length, it has no orientation, it only has its presence. So, 0th dimensional vector space or R0 can be the origin only, it is a point. The point only exists. It is mere existence of a point which can be thought of a vector space of 0 dimension. Why it should be a vector space? Because a point, if we add another, if we multiply with something, it will still remain a point, it has no dimension, its length is 0, it cannot be increased. Also, if we add a point with a point on that same location, I draw a point, I just add another point on exactly, sorry, this is this computer screen is not working, but I can have a point here, I can add another point over this and it will be the same point. So, it is also a vector space, I can multiply and I can do linear combinations here. Now, this is 0th dimensional space, which is origin or merely just a point. What will be R 1 is a single dimensional vector space. We can think of a vector along x axis or vector with length only. It has no inclination, no orientation. I consider there is only x axis and any vector along this is R 1. Why? Because if I try to express this vector, I only have to write one component, say 3, it is 3 meter or 3 centimeter or 4. This should be, this only one component should be able to express the entire vector, because I am only measuring along one particular axis. Now, if we see R 2, and this is very real life like, we do lot of 2D approximations in many cases, and this is x axis and this is y axis, and any of these vectors belong to, all these vectors belong to R 2. So, vectors which are member of vector space R 2 or real coordinate space R 2 has inclination with 2 axes. It has an inclination along x axis some theta, it has some inclination phi along x axis, of course, theta plus phi is 90 degree, and we can get a length along x axis, we can also get a length along y axis. We can express this vector as a 1 b 1, where a 1 is along x axis, b 1 is along y axis. So, the components required to express this vector is 2 when it belongs to R 2. Now, let us see what is in R 3, and that is, we again can write it down very clearly, vectors that has inclination with 3 axes. So, for example, if I have a vector like this, this has some inclination here, some inclination here, some inclination here, and it has some length along each of the coordinate axes. We can express this at a, b, c, where this is basically a I plus b j plus c k, and therefore, anything belonging to R 3 should have, which belongs to R 3, this belongs to R 3, should have 3 components. Now, anything belonging to R 2 has 2 components, anything belonging to R 3 has 3 components, anything belonging to R 4 should have 4 components. And how will it be? How to perceive a vector which is a member of a 4-dimensional real coordinate space, or what can be a 4-dimensional real coordinate space? We can think of something. This is say this we cannot visually perceive it, but we can try to think how to, or we can try to perceive it in a different way, correlating with our visual perceptions. So, let us think of something that this is an R 3 space, and any vector can belong this. And now, this R 3 space is changing in time, and the best example of 4th dimension is time, we all know even from our science fiction studies. So, this R 3 space will change in time, but there is another R 3 space here that will further change in time. So, with time continuously this space is changing. Now, at one particular time I see a particular vector with orientation A here with certain inclination and intercept A along x axis, B along say B along y axis and C along z axis, which is A B C. Now, this is T 1, this is T 2, this is T 3, and it does not exist there, it only exists in T 2 only. So, we will say that it has these 4 coordinates. This A B C is existent only when t is equal to T 2, at from t is equal to 0 up t is equal to T 2, we can see that. So, this is a member of a 4 dimensional vector space. If we see anything which is at T 3 A B C, at T 3 we see some vector with same orientation along x y z axis, that is a different vector. However, both of them are member of the same vector space. So, now we can get a 4 dimensional vector space where there are 4 components to express a vector, what is its length along 3 coordinate axis and probably its the time lapsed when till at which we are observing it. What can be a 5th dimensional vector space? So, for example, this is there are we consider that number of planets are orbiting around a particular star, and this is one particular planet where at one particular time we see this. There are some other planets also, but we are not seeing them in those planets. We are not seeing this particular vector in any other planet, we will see it only one particular planet P. So, in the first observation this vector is not there, the second observation probably not there. Similarly, when we come to pth observation this vector is there. So, we now will say that this particular vector will have A, B, C, T 2, P 5 component, sorry. T 2 P. We need 5 components to express these vectors. If I get similarly, there are with time the coordinate frames are changing here. At one particular coordinate frame we see A 1, B 1, C 1 at time t say T 1 we get something, and this is the observation P 2. So, this will have the vector will be given by a component A 1, B 1, C 1, T 1, P 2. There will be 5 components and this will be in R 5. Now, I can add this vector with this vector and say that there is a resultant vector which probably goes to a different observation a different time, and the distances along x y z axis are different. So on we can think of another set of another star actually. So, this is a planet of one particular star. Now, we can say consider a collection of stars or a galaxy, and one star of the galaxy gives one particular observation of A, B, C, T and P, and this star is say S. So, A, B, C, T, P, S, there are 6 components needed to express that particular observation or particular vector which we are observing there. Therefore, it becomes a member of R 6. So, we can keep on increasing the components of vector and the real coordinate space will increase in its dimension, or the vice versa. We can think of real coordinate space with one more dimension, one more coordinate to observe, and the vector in that coordinate space will have one more component. So, what we can write with increase in dimensions of the vector space or of the real coordinate space, the number of components in a vector increases, and that is how we start from R 0 where there is no component. We basically know it is the origin, it is a 0 vector, and we you can easily call it to be a 0 vector. We do not have to even have to write any component, any component here, any number here, but after that we can say, if we can write one number and it is a member of R1, we can write two numbers, it is a member of R2. So, this means a length from origin, this is the origin, from origin a length 1. This means from origin a length 1 along x axis and 2 along y axis. So, a vector like this. Here we can write 1, 2, 3. So, it will mean, so this is x and y, I will probably write it, that x, y and z. So, 1 along x, 2 along y and 3 along z. So, something like this, a vector like this. Similarly, in R4 we have to write one more component extra. So, as we are increasing the dimension of the vector space, the column vector. So, this if we see from a matrix point of view, this what we are writing as a vector is nothing but a column vector. We are writing it along a column with only one column, and the number of rows is basically the number of component which relates with the dimension of the coordinate space. So, with increase in the dimension, the number of components in a vector space will increase. And now, the next question remains, how long can we increase the dimension of the vector space? We can make one more observation and increase the number of vector, increase the dimension of the vector space or number of components, and that way we can probably increase, not probably, we can in reality increase it up to infinity, or we can think of a vector which has infinite components. That means, at different, along different axes the vector will have different values, and these axes are infinite. How can it be? And now, we think of a infinite dimensional vector space which is a continuous function. Why a continuous function is an infinite dimensional vector space? R infinity, we define it to be an infinite dimensional vector space, and any vector in R infinity will have infinite components. So, if we can think of the function f x, x is equal to x lies between 0 to 1. How many points are within x 0 to 1 range? Infinite points. It is a continuous function, and each point it will have a different value at a specific value. Therefore, it will have infinite values. If I think of a function, if I think of a function x, and this is f of x, say so if this is f x is equal to x, but any f x will give me, if I think of some f x which is like this. Now, if at there are infinite points, if at any point I change the value, I will get a different function, maybe it is following the same pattern, but here the value is changed. So, it is a different function. So, we can get a particular vector here which is given by f x has infinite degree of freedom, or at infinite points its values are specified. So, we get a particular f x. Now, f x is equal to x, this is a function which has the f x has the value same as x, but at infinite points the value is same as x. At any point if it is different than x, then f x is not is equal to x. Now, is it a member of a vector space? We can express it as a vector, because if I write these infinite values, if I try to write out all the values of f x, I have to really write a vector with infinite components. Is it a member of a vector space? So, we can think of another vector g x is equal to sin x. Also, at there are infinite x points, there g x has infinite values. Now, if I add both of them can be used using infinite components. If I add, they belong to infinite dimensional vector space a g x plus b f x, which is a x plus b sin x. This is also a function and has infinite components. If I have infinite points describing x for each point, this particular function also has a distinct value. So, this also becomes a member of R infinity, and therefore, a continuous functions are vectors with infinite components, and they are member of infinite dimensional vector space. So, a continuous function all continuous functions belongs to R infinity. And now, we will start another discussion, what is subspace of a vector space. Vector space, what we are seeing are coordinate spaces are vector spaces, and they can have infinite members there, and they only say that what is the dimension of the vector. Based on the dimension of the vector, we get what what is the dimension of the coordinate space. Based on the coordinate space dimension or physical space dimension, we will say what are the number of components in a vector, and if the number of components matches with the dimension of the vector space, then we will say that this vector, particular vector, belongs to nth dimensional coordinate space or Rn. Now, we are interested in some specific properties of vector space. Why are we interested in that? Because we started discussing with the solution of the equations Ax is equal to 0 or Ax is equal to b when there are infinite solutions. Now, if these infinite solutions belong to certain vector space, and we will be interested to see how is the vector space, but that cannot be R infinity. If it belongs to R infinity, then if x has say 10 components, or it is not R infinity, that should not be Rn. If x has 10 components and I say Ax is equal to b as a solution which belongs to R10, it definitely belongs to R10, but then it can be any vector in R10, it does not tell me anything about the nature of the solution. If I can say that Ax Ax is equal to b has multiple solution, and all these solutions, of course, they are member of R10, but they follow a particular criteria, they belong to particular subspace inside R10, that will be of interest to me. Then I can identify the nature of the solutions in that particular equation, like I have Ax is equal to b and how will be x, that becomes my question. So, if A is m into n, x should belong to, there will be total m rows and n columns. So, x should belongs to Rm, x should belong to Rn rather. Let us do it like this. If A is equal to m into m, A has an order m into m, x must belong to Rm, but Rm is collection of all vectors in that particular vector space. So, where x is belonging, what is the particular nature of x when I am writing x is equal to b, that interests me more. So, what we should start looking into is what is a subspace. Vectors coordinates, real coordinate space, or a larger vector space, or a universal vector space has all vectors of that particular dimension in that Rn, but what is the smaller space or subspace to which the solution of x is equal to b lies, and we will go to the next definition called what is subspace of a vector space. And subspace, as the name suggests, is a smaller subset of that vector space. Subspace of a vector space is a non-empty subset that satisfies the requirement for the vector space. Linear combinations stay in the subspace. So, it is also a vector space, but it is not the real coordinate space, it is a smaller part of the real coordinate space, and if we can do linear combination like add two vectors, that will also rely on that smaller part of the vector space, or if I multiply a vector space with another, that will also lie there. For example, if we can think of this is R2, and we can think that this is a subspace here. So, if I take a vector and multiply it with some constant, this will also lie in that particular subspace. How will it happen, that we have to see, or if I take a vector here and add it with another vector, the resultant should also stay in that subspace, and then we call that this is a subspace of R2. And we will see eventually that all this solution Ax is equal to b in case of infinite solutions lie in a particular subspace. We will see it in the subsequent classes. Thank you.